Hello, everyone. Welcome to the ILTA Physics Problem Solving Lecture. Today, we are going to study acceleration together. Acceleration is the physical factor that changes the velocity of a moving object. The graph below shows the change in velocity of a moving object over time. It represents the motion of an object that starts from rest, meaning its initial velocity is zero, gradually increases its speed over a certain period, maintains a constant speed for a while, and then rapidly slows down over a short period to come to a complete stop. As shown here, acceleration is an important kinematic quantity that expresses how quickly an object's velocity changes over time. The problems we will solve today involve various scenarios using the definition of acceleration, the change in velocity during accelerated motion, and the resulting change in position, which we call displacement. Since accelerated motion plays a vital role in the study of object motion, there are many different types of problems. It is important to understand the core concepts of these problem types and organize them well. So first, let's briefly review the basic concepts and kinematic equations needed for accelerated motion. The physical definition of acceleration is the rate of change of velocity over time. And motion, where the velocity of a moving object changes over time, is exactly what we call accelerated motion. The type of accelerated motion we are dealing with here is uniformly accelerated motion. This means the object moves in a single direction without changing its direction, and while the magnitude of the velocity changes, the rate of change, the acceleration, remains constant. Let's understand the physical concept of this uniform acceleration through graphs. The first method is a motion diagram. Uniformly accelerated motion is represented by dots that get further and further apart, as shown in the figure below. In other words, it is motion where the magnitude of the velocity is gradually increasing. Since a motion diagram marks the position of an object at regular time intervals, the fact that the gaps between positions are getting larger means the object moved faster during that same amount of time. However, in the uniform acceleration we are discussing, the acceleration itself maintains a constant value. Second, in a graph showing the change in acceleration over time, uniform acceleration always shows a horizontal line at a constant value. What's interesting here is that the shaded area, which represents the product of time and acceleration, is equal to the change in velocity during that time. Third, if we graph the change in velocity for uniform acceleration, it is expressed as a linear straight line. The figure below shows a case where the velocity increases as time passes. There are two key physical meanings to this graph. First, the slope of the line is the acceleration. Second, the shaded area under the line represents the change in position or displacement. Finally, the position-time graph for uniform acceleration appears as a quadratic curve. In this case, the slope of the tangent line at any given point in time represents the instantaneous velocity at that specific moment. No matter what conditions or methods are used to describe the motion in an actual problem, you must understand that it refers to uniformly accelerated motion. Now let's briefly summarize these details into quantitative formulas. These are the kinematic formulas for the quantitative relationships of uniformly accelerated motion. Since I covered this in detail during my theory lecture, I'll just summarize the resulting equations here and move on. To keep the formulas simple, we will often assume the initial time is zero when calculating time intervals. So we will simply use t to represent the time interval. First, by definition, acceleration is calculated as the rate of change of velocity over time. That is, the final velocity minus the initial velocity divided by the time interval. Since we are dealing with uniform acceleration, we assume this value is a constant. The change in velocity for this type of motion can be calculated by rearranging the definition of acceleration. It is the product of acceleration and time. Therefore, the final velocity equals the initial velocity plus acceleration times time. Next, the change in position, the displacement, is the shaded area on the velocity time graph. This is the result of two components of motion. To be precise, it consists of the v(I) times t part, shown as the rectangle in the graph, which represents the constant velocity motion if the initial speed were maintained. And the other is 1/2 t squared part, which represents the additional displacement due to the change in velocity from acceleration. Therefore, the displacement due to accelerated motion is calculated as v(I) times t plus 1/2 t squared. Accordingly, the final position of the moving object is the initial position plus the displacement from the accelerated motion. This is organized into a slightly complex quadratic equation with respect to time. Here, if the initial position is 0, meaning we set the starting point as the origin of our coordinate system, the first term disappears, and the formula becomes a bit simpler. If the initial velocity is also 0, meaning it starts from a state of rest, it simplifies further into a basic quadratic expression. Now, let me give you an important tip that you can use very effectively when solving actual problems. If you know both the initial and final velocity of a moving object, you can calculate the average velocity using those two values. Since average velocity is literally the average speed of the object during the time interval, the displacement can be calculated simply as the average velocity times the time interval. In many problems, the initial and final velocities are known, so using the average velocity to find displacement is often much simpler than using the complex quadratic time equation. Finally, by combining these various equations, we can derive a formula for the relationship between velocity and displacement that does not include the time variable. If a problem does not provide information about time, approaching it with this velocity-displacement equation is a great strategy. If you don't fully understand the meaning of the physical relationships explained on this page, please make sure to watch the related theory lecture first to grasp the uniform acceleration equations before returning to these problems. Now let's solve some problems related to uniform acceleration. Problem 28 is a calculation regarding the rapid acceleration of a pike. It is said that a pike can accelerate from rest to a speed of 4 meters per second in just 0.11 seconds. The question asks for the acceleration and the distance traveled during this time. We will solve this by applying the definition of acceleration and the displacement formula. Acceleration is the change in velocity divided by the time interval. From the problem, the initial velocity is 0, the final velocity is 4 meters per second, and the time interval is 0.11 seconds. Calculating this gives an acceleration of 36.36 meters per second squared. The distance traveled, or displacement, can be found in two ways. First, using the formula with initial velocity and acceleration. 1/2 times acceleration times time squared, which gives 0.22 meters. In this problem, since it says the pike started moving from rest, please keep in mind that the initial velocity is given as 0. Alternatively, we can calculate it using the average velocity. Since the initial velocity is 0 and the final velocity is 4 meters per second, the average velocity is 2 meters per second. Multiplying this by the travel time gives the same result of 0.22 meters. Please practice using these formulas efficiently based on the given conditions, just like we did in this problem. Problem 29 is a basic question about uniform acceleration. However, it involves converting units, so let's look at it together. A car at rest accelerates to 60 miles per hour in 10 seconds. The problem asks us to find the acceleration, express it as a ratio of the acceleration due to gravity, and find the distance traveled during that time. Since the speed is given in miles per hour, let's first convert it to meters and seconds. 1 mile is 1,609.34 meters and 1 hour is 3,600 seconds. By multiplying and dividing, the car's speed becomes 26.82 meters per second. Now, using the converted velocity to calculate acceleration. Since it started from rest, the initial velocity is 0, so the acceleration is 2.68 meters per second squared. To express this as a ratio of gravity, we divide by 9.8 meters per second squared, which gives a ratio of 0.27. Finally, for the distance traveled, if we apply the displacement formula using the average velocity we mentioned earlier, we get 134.1 meters. Since 1 meter is 3.28 feet, converting this back to feet gives us 439.8 feet. Although this is a basic problem, it includes unit conversions, so please practice until you are comfortable with them. That's all for today's lecture. You all did a great job. I'll see you next time.